Hello, everyone. Can you see my hand? There it is. Hello, 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 hello. How are you all today? Get my headphones in. I'm the kind of person that I do not like to waste time, so I don't just sit there and stare at the screen waiting for the thing to start. I've got to fix something or, do something. So here I am. Hope you all are doing well today. Getting this cord all freaking straightened out. Long cord. It's all tangled up. Hold on. Ugh. Okay, here we are. So let's see who is here today. Ben and Katerina. So thanks for coming in. Yes, we're going to talk about potential energy today. Did I say power? No, I just said potential energy. We'll touch on power just a little bit before we get into potential energy. So let's write this on the board. What's this crap? First thing we'll start with is power. So what do you think of when you think of power? I'll put my music on while you are thinking of an answer. Power. do something. Yep. Power involves work. So when you think of something that's powerful, like a car is powerful, a rocket engine is powerful, an airplane is powerful, you're thinking about it doing work, but in a fast amount of time. It's doing it quickly. So it's work over time, I should say. So it's work divided by time. So how fast can something do work? So you think of anything that does work, like you pushing the lawnmower, you pushing a box across the floor, you lifting a box off the floor and putting it on a shelf. That's work, but how long it takes you to do that work is power. Actually, not how long it takes you to do the work, that's time. But dividing the work done by the time it takes is power. So we call the units for work joules. Time is measured in seconds. So a joule per second is called a watt. So think about your light bulbs. Your light bulbs are rated in watts. If you look at the light bulb, it'll say 60 watts, whatever. There's different types of light bulbs. That's the amount of power it's pushing out in terms of light energy. All right, now, a lot of people think that they say they get their power bill, electricity bill. Power bill is kind of a wrong way to think of it, because the energy or the power you're getting in your house for electricity is measured in kilowatt hours. So K is just kilo. This is 1,000. So it's just a number. So we're talking about a watt times an hour. So a watt is a joule per second. And then we can turn hours into seconds. 1 hour is 3,600 seconds. So technically these cancel out. So what you're measuring in, the only leftover thing you have here in terms of units is the joule. So when you're getting charged by the electric company, you're getting charged for energy. So this is technically an energy bill. So that's pretty much all I got to say about power. There's another way to calculate it. Power is force times velocity. But this is instantaneous velocity. So if you know how fast something is going, let's say a car, and you know the force put into it, the engine is pushing to the wheels, you can calculate its power. So that's it for power. Not much else to say about it. So we will get rid of it and move on to the next thing, which is more important. Well, I guess it's all important, just depends on what you're working on. So let's talk about potential energy. Potential. Potential means that there's something that can be done from it. Yes, that's right, Ben. The amps is the amount of electric charge, joule or coulombs per second. Okay, so when you talk about energy, energy is the ability to do work. Ability to do work. Handwriting is garbage. Potential is stored energy. So somehow we're able to take energy and store it somehow. Right, potential energy on Mondays is usually pretty low. So we're going to talk about two types. First is gravitational potential energy. and the other is elastic. And both of these are what we call conservative forces. Conservative forces means that you can exert the force and the result of it energy can be stored. It's the force always tries to put the object back to the lower energy state. So it's kind of a tricky definition. So I'm just going to say the force, the conservative force, always tries to put the object, I guess, back to lower energy state. I gotta erase this. So think about gravitational potential energy. Well, think about gravity, like force, gravitational force. If I have the ground here and I lift some kind of ball up to this point here, you know gravity is trying to pull it back down. It never fails. People call me when I'm streaming. It's a miracle. So gravity is trying to pull this thing back down to a lower energy state. So obviously on the ground is the lowest energy state for gravity, because you can't fall any further than the ground. Right? When you're on the ground, you're not going anywhere, you're not going any lower, unless the floor breaks, which if you're on the dirt outside and the actual earth, you're not going to go any lower. So this is the lower energy state. And up here, higher energy states. Oh, the handwriting is awful. Damn. Exactly. That's right, Ben. So when the roller coaster is at the top of the hill, it's got high energy, and gravity is going to try to restore it to the lower energy state. That's why water runs downhill. That's why everything falls. So let's say I do work. Say I do work on this thing. I lift it up from the ground. Let's say this is a mass of M. M is 1 kilogram. And I lift it up to here. And let's say it is 1 meter off of the ground. How much work did I do? Work is going to be the force times the distance times the cosine of the angle between F and D. I did this last week. So the force is going to be the weight of the mass. The distance is 1 meter. And the cosine of the angle between them, well, I'm applying the force this way and the displacement is this way. So the cosine would be, or the angle would be 0 degrees. We know mass is 1. So we know it's 9.8 times 1 times 1. So it's just 9.8 joules. That's how much energy it took. That's how much work I did to get it up to its elevation, 1 meter off of the ground. Well, if we look at this equation again, and we just plug in what it is a little bit clearer here, mg is the force, d is the height, and we know that the angle would be 0, so we have mgh. Well, this is then the potential energy due to gravity. So mgh is U sub g. I'll do that in red because that's really important. And what is U sub g? This is gravitational potential energy. And you can't see that, can you? Doggone it, this stupid thing. Hold on. Well, I might as well just rewrite it. See if I can move it. That's not very good. Let's just delete it. So here you go again. So you have MGH. So U sub G equals MGH. This is gravitational potential energy. So M is the mass, G is acceleration of gravity, H is the difference. This here is the change in elevation. Change in elevation. So you have to set a specific point to be 0 energy, and then you go up to that point or down and you'll have it. So it only works against the gravitational field, MGH. So let's do an example. I'll get rid of all of this. So here's an example. Let's do a roller coaster. And we'll say that this is the baseline of the roller coaster. We'll call this H. This is H over 2. And we'll make this 3/2 H. So if we start here in our cart, we're going over the edge here, we have MGH of gravitational potential energy. So what happens then? Well, when it's going down here at the bottom, there is no more gravitational potential energy because we set this point to be 0 of gravitational potential energy. There is no gravitational potential energy here. That's where we defined it to be 0. So at the bottom, since we have the conservation of energy law in the universe, you cannot create energy, you can't destroy it, it just transforms from one form to another. This is all kinetic energy. That's right, Ben. And kinetic energy is, the equation is 1/2 of the mass times its velocity squared. So due to the law of conservation of energy, MGH has to equal 1/2 mv squared. Right? Because all this energy stored up due to gravitational potential energy stored in this cart will turn into the energy of motion at the bottom. So you can see that the masses cancel out and you get 2gh equals v square root. Now I want to show you something pretty cool. Do you remember, let's see, this is, let's see, final squared, this is squared. Let's see, final squared is velocity initial squared plus 2AD. Remember that kinematics equation? Well, up here, the initial velocity is 0. It's not moving until it's pushed over the edge. So this is gone. So velocity final then equals 2AD. Well, what is A? A is G, and D is H. So VF equals the square root of 2GH. So you can see these equations are the same. So we just derived a kinematics equation from energy. So you can see how they're related. Time for a cookie break. Now, what will be the velocity here? Hey, Genesis. What's the velocity going to be at the top here? Well, we have this kinetic energy at the bottom. The kinetic energy at the bottom has to turn into potential at the top plus any more kinetic at the top. Since we're not back at our original elevation here, we're still going to be moving, right? That's the whole point of a roller coaster. You don't just stop at the top of a hill. It's got to be moving still. So we have 1/2 of the mass times its velocity squared, which its velocity is this here. And then we square it. And up the top here, it's going to be mgh over 2 now, plus 1/2 mv top squared. So this, let's just get rid of the masses right off the bat. Get rid of them. The square root of 2gh squared is just 2gh. So 1/2 of 2gh equals gh over 2 plus 1/2 of vt squared. And look, the 2's cancel out, the halves cancel in every problem, or every term. So you get 2gh equals gh plus v top squared. So 2gh minus gh from the other side equals v top squared. So we get gh equals v top, square root of that. So that's how fast this thing is moving when it gets to the top here. It's still moving. Hey Pegasus, thanks for coming in. So if you know the initial height, you'll know how fast you're moving when you get to that first hill. And that's assuming no loss of energy due to friction or air resistance, etc. Now, when we go to the bottom here, same thing. We get to the bottom. This is supposed to be on the bottom. About to sneeze, hold on. It'll go up to about here, and then it'll stop because it's maxed out energy here. It doesn't have any more energy than this. So that's why these roller coasters will have these little chains that will, you'll hear it click, and they'll go click, 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 click. So it has to have input of energy from a machine to get it up to this maximum height here. And then it can roll down to the bottom again. So that's pretty much the law of the conservation of energy. Any questions about that? off half the problem down here. Ben's right. Science and math have to come together for engineering. That's right, man. All right. Let's go on to elastic potential energy. So this would be a spring or a rubber band. It's a spring. So let's just do a perfect ideal spring. So you think about it, if you have a spring, and how do they account for different weight due to differences in riders? Let's see, let me go back. If I can go back. Hopefully it's still there. Yes. What do you notice about mass in all of these terms? Like here. Mass, mass, mass. Doesn't matter. It does with friction and stuff. And they account for that. But in the pure sense, if there's no loss due to friction, mass is irrelevant. Pendulum, yes, but pendulum has potential energy. Let's talk about a pendulum. Hey, Shocker Cat. Pendulum's a little bit more complicated. So let's say we have a mass here, and we offset it like that, so that it's going to swing through this arc. Back and forth, right? So up here, well, at the bottom here, this is all kinetic energy. When it's at its maximum height here, it's all gravitational potential energy. So depending on how much work you do to move this thing, the ball, up to the other side will determine how fast it'll be going at the bottom. So energy is just transferred from potential to kinetic and back and forth. So all potential, it turns into all kinetic at the bottom, and then you start losing kinetic energy as you get up to here, and you have all potential again. And then it goes back. All right, let's talk about spring, elastic potential energy. Springs. So if you think about a spring, and you stretch the spring out, stretch Stretch the spring, stretch the spring. What's the spring going to want to do? The spring wants to go back to its original length. It doesn't want to be in that high energy state. It wants to go back. So that's why springs are conservative forces. So the potential energy of a spring equation is 1/2 K delta X squared. K is the spring constant. And this delta X is how much the spring is stretched or compressed. Dill hole. So that's all it is for that. Now we can do a problem involving this. Let's do one. I'm going to get rid of this. Go to the problem here. So let's say we have a mass top of an incline that's going to slide down, call it mass M, and we have a spring here, spring constant K. And this is a height H. How far is this spring going to compress when that mass hits it? How far will spring compress? So what do we have here? What kind of energy do we have at the top if our initial velocity is 0? Hey Greg. It's all potential, right? So we have potential energy. So I should do this. Actually, I want to show you the mechanical energy equation. So it's the kinetic energy, initial, plus potential energy, initial, plus any external work, and that would be like friction. It's going to turn into kinetic final plus potential final. And let's say that we lose no, let's forget it. Let's not worry about losing energy. No friction, no loss of energy. So you go through this equation to see what you have initially. At the initial here, you don't have any kinetic energy, so that's 0. But you have potential due to gravity. We said there's no friction, so we'll get rid of that. And like when it hits this spring and starts to compress, it's going to compress it to the point where it doesn't move anymore. So it's not going to have any kinetic energy final, but it will have spring potential energy final. So the gravitational potential energy is mgh. Spring potential energy is 1/2 K delta X squared. And now we can solve for delta X, that's what we're looking for. So it'll be 2 mgh over k square root. So that's how far that spring is going to compress. So if you were an engineer and needed to stop a, I don't know, roller coaster ride, cart, by a spring, which they don't do, but let's just say that you were, you'd have to take into consideration the mass of the cart and the people in it and design a spring that could handle that. And you can see why they don't do it like this, because of the mass here. You don't want to have to have a specific mass that can't change in your scenario. Then you wouldn't be able to have people write it. So that's why they don't use springs to stop carts with people in it. Any questions on this? Nope. Yeah, right to the hole. Okay, so it's 2:40. I've got to call back this person that called me, and Physikē will be on at 3. So we'll stop here, and next week we'll talk about momentum. Momentum. Momentum, it's mass times velocity. I'll give you a hint. Alright, thanks everyone for coming in. Let's see who's here. Dillhole, Greg, Katarina, Pegasus, and Shaka Cat. And if Ben King's still here, he's probably watching. Thank you all for coming in, and I'll see you in Genesis. I'll see you in Physikē's stream very briefly. Thanks, Ben. We'll see you soon.
10.
Let's go for main engine start.
6, 5, 4, 3, 2, 1. And booster ignition, liftoff of Space Shuttle Discovery, taking the space station to full power for full science.
This is Mission Control Houston.
Discovery roll program. Roger roll, Discovery.
Discovery's roll maneuver is complete. It is now in a heads-down position on track for its flight to the International Space Station. Discovery flying 365 miles per hour, 1.5 miles in altitude, 7 miles downrange from the Kennedy Space Center. Discovery's engines are throttling down as the orbiter passes through the area of maximum pressure on the vehicle.